I'm going to talk about Laguerre minimal surfaces. I want to talk about a way of constructing such surfaces using congruence of lines. Okay, and it's a joint work with Rafaela do Prado. So, Laguerre minimal surfaces are critical points of this functional, and as far as I know, they were studied by Blaschke in the 1920s. And now there's some interest in them. There are applications in architecture, but they're critical points of this function. Okay? And the way we're going to construct such surfaces actually generalizes a method by Ribocourt a long time ago, where he showed that the middle envelope of an isotropic congruence of lines, if it's not just generated, is a minimal surface. Okay, so I will have to explain these terms, okay, because I think they don't appear in modern books of differential geometry of surfaces. And I think many people that work with minimal surfaces actually don't know this result. So even if you don't care about Laguerre minimal surfaces, I think it's a nice thing to know about Ribocourt's result. Okay, so how are we going to do this? There are two basic ingredients. The first one is we're going to look at the space of oriented lines in Euclidean space as the tangent bundle of the unit sphere, right? And then we can use a little bit of complex geometry, and holomorphic coordinates will help us in this work. And the other ingredient is just the classical theory of congruence of lines. And I'll give a quick review of that here. Okay. So what we have to do is just very simple. Mix both ingredients, and actually we're going to construct congruence of lines. We're going to define them in terms of holomorphic, anti-holomorphic, and more generally harmonic maps. And see what happens. Okay. So the way we identify the space of oriented lines with the tangent bundle of the unit sphere is actually very simple. I'm going to draw a picture to explain things. So, if you have the Euclidean space, you fix origin, and if you have an oriented straight line, so you can take a unit vector, it gives the direction of the line, okay, and you can choose. You take the point closest to the origin, and this defines a vector, B. So this is a unit vector, and you have A and B orthogonal. So if you have an oriented line, you can do this, and if you have a pair of vectors satisfying this, you can associate to this pair of vectors this oriented line, okay? And this is basically the tangent bundle of the unit sphere, right? And in this work, I'll use coordinates, and the natural coordinates here. If you think of the unit sphere, here the horizontal plane passing through the equator. This is the south pole. So this will be a complex coordinate, okay, associated to this point of the sphere. And I'll write tangent vectors like this, okay? I hope it's clear. So this is the map. I was not sure I'll have a blackboard, so actually it's the same picture. Okay. So with a little bit of geometry, elementary geometry, you can figure out if you have a pair of complex numbers, C eta, then you can associate to this pair, which is basically a tangent vector of the unit sphere. You can associate an oriented line, and the first two coordinates in the horizontal plane, so z is a complex coordinate, is given by this. R here is just an affine parameter. Okay, so you go up and down in the oriented line. And the vertical coordinate, I'll call this t. Okay, so if you have c and eta, you have this oriented line. This is the expression. And, okay. So a congruence of lines here will be a local section of this bundle. Okay. So actually what I'm going to do, I'm going to consider, so C is basically the point in the sphere, and I'll write eta as a function of C. Okay, so I have a two-parameter, and where this map is smooth. So I have a two-parameter family of oriented lines. Okay. Now I'm going to talk about a little bit about some classical concepts. Basically, this limit and middle points. Okay, so I'll try to draw a picture. So you can imagine. I won't try to draw a two-parameter family of lines because it's going to be a great mess. So I'm going to draw like a surface. Such that each line of this congruence of lines passes through the surface. Okay, so if we take a particular straight line, I'm going to call it L. We can imagine curves here in this surface, and then we can consider the ruled surfaces belonging to the two-parameter family of straight lines. And for each curve, you imagine here you have an associated ruled surface. I don't know how to draw this. Okay, it's a ruled surface. So let's think about one of these. Okay, then when you have a ruled surface, you have a restriction line associated to it. Okay, and in case you don't remember, one way of thinking about this, you consider rulings approaching this fixed generator, and for each ruling, you imagine that you have the common perpendicular to both rulings. Okay, and then the point of the restriction line passing through L is actually the limit of this point in L of this common perpendicular. Okay, so that's it. So for each curve you have here, you can associate a point of L, which is the point of the restriction line that passes through L. Okay, and so when you have a congruence of lines, you can consider all curves here passing. You fix a generator, and then you have another ruled surface, this red one, and then you're going to have another point. Generically, you have another point, which is the point where the restriction line touches L. Okay. So when you vary all the curves here, you consider all the ruled surfaces with rulings belonging to the congruence of lines and passing with L as a ruling. Then, in general, what you get the family of these points in general is a segment, right? It's a segment. And the extremities of this segment are called the limit points, and the middle is called the middle point, okay? So I hope it's clear. Okay, oops. Yeah, that's basically what I tried to explain. And the picture, I didn't know. Yeah, well, it's that picture, basically. Okay. Sorry. And we have that. Now I can tell you what isotropic congruences are. Well, there are very special types of congruences for which this segment then degenerates to a point. For each ruling that you consider, for each line of the congruence of lines that you consider, this segment degenerates to a point. Okay? So when this happens, classically, this is called an isotropic congruence of lines. And Ribecourt discovered that you can do the following constructions. I think it's a very nice construction. So basically, what he did is he considered an isotropic congruence of lines, and then I'll draw a line of this congruence, call it L. And then suppose associated to this line you have the middle point. Okay? And he considered the plane orthogonal to L and passing through M, the middle point. And this is called the middle plane. Okay? And what he did, he considered the envelope of this two-parameter family of planes, right? And sorry if my picture is very bad. Okay, suppose, call this S. There's a surface such that for each point here, the middle plane is tangent to it. So this is called the middle envelope of the congruence of lines. And what Ribecourt discovered is that if you start with an isotropic congruence of lines, the envelope is a minimal surface, right? That's what he did. And I think it's a beautiful result. It used to be known. So, what I'm going to do now, very quickly, is to see what happens if we start describing a congruence of lines in terms of these holomorphic coordinates for the tangent bundle of the unit sphere, and see if this big F here has nice analytical properties. This is the question. Is the congruence of lines associated to it interesting? Okay? So let's see what happens. It's basically a lot of calculations. I won't do them here, of course. But, well, we can think of a congruence of lines locally as U via real parameters R also. So this is the surface. All those straight lines pass through X, okay? And then you have R times N gives you, R is just an affine parameter to go along the line, and N gives you the direction of the straight line. Okay, so locally you can write a congruence like this, and let's go. Okay, and then there's the classical way of computing things. That's the way I used, was this Kummer in 18 something, I don't recall right now. And basically you have two quadratic forms, and you can compute this middle points, limit points in terms of these quadratic forms. Okay, so the limit points are given by, here. So this is just the metric in the sphere, and this is combination here. There's a combination between derivatives of x and n. Okay, right? So then the limit points are the roots of this quadratic polynomial for r. Okay, and after some computations, the middle point is, you have this expression. Okay, and when you plug in x and n given by these expressions, this is just the usual expression for a point in the sphere when you use stereographic projection. And this, the ugly expression I showed you in the beginning, if you take, instead of eta, you take this big F, you get this. Okay? So when you compute, you get nice expressions. This coordinate, this is how far you have to go, starting from x here to the middle point. Okay, so this Rm is this distance. Okay, and you have this expression, and the distance between the limit points. Okay, if you have, say, for a straight line here, have one limit point here, another here. This distance is given by this expression, and it's a nice expression because here you can see that this is 0. It's the case where you get isotropic congruences. Okay, exactly when phi and psi are the real. You have f, and it's real and imaginary parts of f. Oops. I have to run. So you have the Cauchy-Riemann equations here. Okay, so if f is holomorphic, you get an isotropic congruence. It's okay, this is a Cauchy-Riemann equations. And then it's a natural question to see what happens when instead of holomorphic, you put f as a harmonic map. Okay, harmonic map from the plane, an open set of the complex plane into the complex plane. And this function, I'll call it h here, is going to be the support function of the middle envelope of the congruence. This is very easy to see because here, this is our origin. Okay, so this x goes here. And this distance actually is the distance, this is Rm, okay? And exactly it's the distance from this plane to the origin, which is classically the support function. So the support function is going to be this. And the Euler-Lagrange equation for the Laguerre functional is Laplacian of h over k. H is the mean curvature, k is the Gaussian curvature. Is a harmonic function. H over k is a harmonic function with respect to the spherical metric. Okay? This Laplacian. So in terms of the support function, h, this equation becomes this one. Okay? Because this inside is just expression of h over k in terms of the support function. And if you compute, if you believe me, if you take f harmonic, then h is always a solution of this equation. So if you start with f harmonic instead of holomorphic, you generate, by the same process, you generate Laguerre minimal surfaces. And yeah, that's it. Okay. And well, special case, if you have f holomorphic, you recover Riemann-Coulomb. Okay. And a natural question is what happens if f is anti-holomorphic? Actually, it's kind of nice because you have a geometric result. If you start with F anti-holomorphic, the surface you obtain is a Laguerre-minimal surface of spherical type. What is a Laguerre-minimal surface of spherical type? Actually, when you have a Laguerre-minimal surface, let's say sigma, you can consider a congruence of spheres tangent to sigma and with radius h over k. Okay? And in general, the other envelope of this congruence of spheres, if you start with a Laguerre minimal here, this surface is also Laguerre minimal. It's actually very similar to what happens with Wilmer surfaces. Okay? But there is a special case when you start with a Laguerre minimal surface and the other envelope is actually a plane or part of a plane. Okay? And this is called Laguerre minimal of spherical type. So if you start with F anti-holomorphic, then what you get is a surface such that, a Laguerre minimal surface such that when you consider this congruence of spheres, the other envelope is contained in a fixed plane. Okay? So to finish, I'll just show you some examples. If you start, say, with F given by this expression, you get a surface of this type, which actually is a Dupont surface. Lines of curvatures are circles. I didn't know that some Dupont surfaces are also Laguerre minimal, but turns out they are. Another example, if you start with F, log of Z plus 1 over Z bar squared, you get a periodic surface, okay, a one periodic surface, which is kind of nice because the picture is very bad here, but here there is a curve here that repeats itself, and it's a cycloid. It's a nice curve here. Okay, and the last example, yeah, just for fun, you can take like this F as this thing, and you get a surface which looks like this. It's very easy to construct them. You just plug in F, and you have an expression for the Laguerre minimal surface. Okay, so it's a very simple construction, and I think it has a geometric flavor, and it mixes one way of thinking about the space of oriented lines, which is very interesting, using complex geometry, and classical theory, which is I think it's a very nice subject also. Okay, I think that's all. Yeah, that's all. Sorry, I didn't put thanks in the end, but thank you very much. Valeu. Desculpa aí o X aí, sim.